We've already talked about what Turing machines are and described how they work. In this video, we're going to talk about some techniques for programming Turing machines. The first thing we'd like to be able to do is recognize the left end of the tape. As you know, we can't move our tape head to the left beyond the left end of the tape, and there's no way built into the definition of Turing machine to detect when we're at the left end. But it would be useful to be able to do this. So what we're going to do is we're going to put a special symbol. We're going to create a new symbol that's not already in our alphabet. We'll use the $ for this use. And we want to squeeze it in somehow on the left end. And we'll do this by shifting our input over one cell to the right. So let's say we have a particular Turing machine where our input alphabet consists of A's and B's. As the first step of computation, what we want to do is shift all these input characters over one and put a new symbol, the $, on the left end. And then we can start our main computation. And as we move our head left and right, we can watch for the left end of the input. So here's a Turing machine that I suggest will do that. So let's go through and take a look at this Turing machine. Here's our initial state, and here's where we continue with the rest of the computation over here, and we don't know what that might be. But we start by looking at the first letter on the tape. If it's an A, we move to the right and we replace it with a $. And then, okay, we've gotten an A, so that's why I've labeled this state A. What we do then is we scan, and in the next step, we write an A. Regardless of whether we saw the second character is an A or a B, we're going to write an A. If the second character is also an A, then we're going to keep in this state and we're going to keep copying A's. Okay? So this state A simply means that the last character we saw to the left of the head position was an A. And if we see a B, we move down to this state. On the other hand, if we started from our initial state and we saw a B, we would replace it with a $, and then in the next transition, we would write a B, either here or here. And finally, when we see a blank, we've reached the end of our input. And if we had been looking at a B last, we write a B, we write that final B. And if we had been looking at A's, we write that final A. And we move back to the left. And then we scan over A's and B's without changing them toward the left until we hit our $. We replace the $, with itself, and we move to the right, and we're positioned right here, and we're ready to start the main part of our computation. Now, I assume this is correct, but like any Turing machine, it's subject to human error when it's being created. But take a look at this, and I think you'll see that it is correct and does exactly what we want it to do. So this is an example where we have sort of overcome one of the limitations of the Turing machine, that we cannot see the left end of the Turing machine, of the tape's left end. We can't detect that. There's no mechanism built into the formal definition of Turing machines that allows us to detect the left end of the tape, but we can use this programming technique to achieve the same result. So just how much programming on a Turing machine do you need to do? Well, the answer is you need to do enough to get the idea of how they work, and also to convince yourself that any program that you might want to write can be implemented on a Turing machine. So you need to program these Turing machines until you are convinced and comfortable with the fact that any algorithm can be programmed on a Turing machine. So I want to look at this analogy of writing programs from high level to low level. On the left side, you have traditional computers, okay? Going from the lowest level implementation of an algorithm in machine code, okay, we might write out the opcode here in binary, and that's a pretty low level way to express an algorithm. The earliest computers were programmed like this, and it was very tedious and error prone. And then we invented assembly code. And assembly code allows us to write algorithms in a higher level form. And the translation from assembly code into machine code is relatively straightforward. And at this stage of the development of computers and computer programming, programs suddenly got very interesting, and we could write lots of different algorithms in assembly language. After that, we figured out that it's nicer to write our algorithms in even higher level code. And here I have a sample programming language. It could be Java or anything. But the idea is we're now expressing our algorithms in a notation that's even more intuitive and easier to use. And while this may take hours and hours to get the program done, something like this reduces the coding time to minutes or even seconds. And then at the highest level, we might have even a nicer notation. And you'd like your programming language to have the ability to take care of notation like this. Here we see the algorithm as it is most perfectly expressed, ideally with no implementation details, okay, and some sort of a high-level pseudocode. And so algorithms can be expressed all the way from machine code to a high-level code, and the further down this hierarchy you go, or the further up toward machine code, down in terms of detail, the more dependent you are on the actual implementation. Now on Turing machines we have a similar kind of hierarchy. At the very highest level of specification, we specify our algorithms with no implementation details. And in fact we have no Turing machine specific details at this highest level of specification. At the lowest level of programming our Turing machine, like machine code, we have a lot of detailed implementation information. What are our states? What does the transition function look like? It's kind of difficult to program a Turing machine at this level. The complete Turing machine specification can be quite long and prone to errors. There's an intermediate, or there are several intermediate stages of specifying our algorithm. But one important way to look at the algorithm is where there's some implementation detail, but the actual states and transitions are sort of abstracted away. Tape head movement. But we're doing it at a slightly higher level. So we might say things like, move the tape head all the way back to the beginning, or move the tape head to where the second part of the input begins. We also talk a little bit about how the data is represented without talking about how we're going to use states and transition functions to interpret and modify that data representation. You could even imagine a compiler that compiles a particular programming language like C or Java, not into machine code for your favorite microprocessor, but into states and transition functions for your favorite Turing machine. In the next example, we're going to build a Turing machine to recognize the language 0 to the n, 1 to the n, 0 to the n. This language is decidable, so what we should really say is we're going to create a Turing machine to decide the language. When given this as an input, a string like this with some zeros and ones and zeros, it will either accept or reject. But since it's a decider, it will never loop. It will always halt. And this language is not context-free. Okay, we looked at examples like this when we talked about using the pumping lemma to prove that languages were not context-free. So, by showing how we can decide this language with a Turing machine, we will show that the set of decidable languages is a proper subset of the set of context-free languages. Well, in an earlier example, we created a Turing machine that could recognize this language, 0 to the n, 1 to the n. Or more precisely, I should say, it could decide that language. And it also had the property of turning the zeros into x's and the ones into y's. So the new programming technique we're going to introduce here is that we can use one Turing machine as a sort of subroutine for another Turing machine. So if we have a Turing machine that does one task, and that task is useful, we can incorporate that Turing machine into a new and larger Turing machine that we're building. So our goal is to recognize 0 to the n, 1 to the n, 0 to the n. And this is somewhat similar, so we're going to use that as a subroutine. So our Turing machine will have several steps. In the first step, here's a sample input on the tape, and we want to accept this input because it is a part of the language. Well, in the first step, what we're going to do is we're going to scan the zeros and the ones, and we're going to turn them into x's and y's. We might have to modify that Turing machine a little bit because it was looking for a blank after the last one, but I think you can see that we could modify it appropriately. So it will modify this input to this, and if for some reason the number of initial zeros is not equal to the number of ones that follow it, then it will reject. So in step 2, we now have this string. What we're going to do is recognize y to the n, 0 to the n. It's a similar problem because we have y here and we have zeros here. So we can position our head right there and then create a similar Turing machine, similar to the one that turned 0 to the n, 1 to the n into x to the n, y to the n. And now we'll take the second Turing machine and use it to recognize y to the n, 0 to the n. And then our final Turing machine is basically connecting these two Turing machines together with a couple of appropriate states to move the heads to the right place. Our first Turing machine, after converting 0 to the n, 1 to the n into x to the n, y to the n, ended with its tape head here at this end of the y's. Well, we need to move the head back to the beginning of the y's before we start our second stage, which recognizes y to the n, 0 to the n. Our next task is to recognize this language. W, which is a string of A's, B's, and C's, followed by a pound sign, followed by that same string again. So the first half has to be equal to the second half. So we essentially have to compare an arbitrarily long string to a second arbitrarily long string to make sure they're equal. This is a very useful subroutine to have in Turing machines because we oftentimes need to ask whether one thing is equal to another thing, or more precisely whether its representation is equal to the representation of a second thing. So the technique that we're going to use here involves introducing a new symbol and using it to mark what we've done so far. So we're going to introduce a new symbol. In this case, we'll use x, and we're going to use it to mark what we've looked at so far. Okay, so let's say our input looks like this: AABAC, pound AABAC. So this is an example where we should accept. What we're going to do is we're going to look at that first A and see that it's an A. We're going to mark it as an X, and then we're going to scan past the first part of the string to the pound sign, and then see that this character here is the same thing. In this case, we have to remember we're looking for an A. We find it's an A, so we mark it with an X. And then we scan back and look at the next character. That's also an A, and then we scan, so we mark it with an X. And then we scan forward until we hit this A and mark it with an X. And then we scan back, and we keep going like that, back and forth. If we hit a B, then we have to scan, and this time we're scanning in a different state because we have to remember that we're looking for B. So we scan past all the symbols till we hit the pound, then we scan past X's until we hit a B. And we keep going like this until finally we've marked all the symbols, and we can announce that, yes, in fact, these two strings are the same. Now, if this is going to be part of a larger Turing machine, we'd like to be able to do this task non-destructively without turning the original strings into X's. We don't want to lose that original data. So what we're going to do is we're going to use a slightly different technique where we mark each symbol, but we're going to use different symbols to do the marking so that we're not going to lose the information of what was there originally. So we're going to add some new symbols. Remember, our input alphabet had A, B, and C in it, so we're going to use 3 new symbols, X, Y, and Z, for each one of those. And the idea is, instead of turning everything into an X, we're going to turn A's into X's, we're going to turn B's into Y's, and C's into Z's. And then later, after we're all done, we can restore the strings, okay, if we're going to be needing them later in the algorithm. So that's pretty simple to do. We just go back to the beginning and scan and change X's back to A's, Y's to B's, and Z's to C's. The details are kind of approximate here, but you get the idea that we can use a number of new symbols to make sure that we don't lose information in this string comparison algorithm. So what we've just shown is that we have a technique for marking symbols and remembering what they are. So we can somehow indicate that we've looked at them, or we've flagged them or signaled them or something, without losing the information that they contain. And so this is a general programming technique that we can use in other situations, and we'll just assume that we have that technique. And in particular, we might want to mark each symbol, and in our notation, it might be more convenient to imagine putting a dot under each symbol. So we've marked A's, B's, and C's with dots. Okay, so in our algorithm, we might say, put a mark under the A, or check the A, put a dot under that symbol. Well, what that really means is an implementation that involves adding new symbols that correspond to the existing symbols that we might be marking, and later going back and changing them. So when I say in future algorithms, mark a symbol with a dot, then you know it's possible using this technique of replacing a symbol like A with another symbol that's different, like A dot here, and then later on treating A dot just like an A, and perhaps turning it back into an A if we need to. So we can use this idea of marking certain symbols with a dot in algorithms, so that allows us to do things like remember a particular location on the tape. So in writing our algorithms, we can say, remember where this was, remember where we were. We could say, mark that symbol with a dot. Okay, and we now know how to do that using a Turing machine primitive operations. And in fact, we could have several different kinds of marks. Here I'm using colors green, red, and blue. So I could maybe place, here our input symbols are zeros and ones, and I might say place a blue dot on this symbol, place a red dot on this symbol, place a green dot on this symbol, place several red dots around. Okay, maybe some symbols could have multiple dots on them. These would all require additional symbols in our alphabet, but we could do that. You see how we could do that? So it allows us to mark any place on the tape that we want to, and we can use different kinds of marks as well. And so we might say, use these things as sort of like pointers. We might, if we want to mark this symbol as something of particular interest, we might say, well, let P point to the beginning of the second string, and let Q point to such, and something else on the tape. Using our techniques of marks, we can implement that using the primitives of the Turing machine.